Hello again, physics friends. Today we are going to talk about 2D polar coordinates. And we might start a little bit by thinking about the motivation for using non-Cartesian coordinates. And one way that you might want to move away from Cartesian coordinates is if you have motion that's non-linear, in other words, not just in the x or the y direction, but that motion is clearly one-dimensional. And here's an example of something along those lines. We have a pendulum attached to a ceiling, and this pendulum has a fixed length, call that capital L, and we can indicate the angle of the pendulum relative to the vertical, and we know that pendulum will move on a circular arc, like so. If we confined ourselves to using a Cartesian coordinate system x and y, then we would have to talk about the motion in both the x and the y directions, even though the motion really is just along the arc. And if we had a way to parameterize the motion along this arc, then it would become a one-dimensional problem. In other words, although the pendulum in principle, an object in principle, can move in 3 dimensions, there's a couple constraints here. One is the pendulum is confined to the plane of the page, and 2, the distance between the pendulum and the origin is fixed. It's always L. So there's an additional constraint. So that reduces from 3-dimensional motion to just 1-dimensional motion. To drive this point home, let's draw out a force diagram for the pendulum bob. So here I'm looking at a force diagram of the bob itself. We are going to have a gravitational force, long-range force of gravity pointing down, and then we'll have a tension force associated with the string, in this case up and to the left. And we have here this angle theta relative to the vertical. So we can write out all these forces. The gravitational force points in the minus y direction, and the tension force has components in both the x and the y direction. In the x direction, the tension force points to the left, minus t sine theta, and in the vertical direction it has an upward component, that's plus t cosine of theta. So our net force has both an x and a y component. Okay. So if you wanted to do Newton's second law in Cartesian, you'd need to deal with 2 differential equations, one for the x and one for the y direction. But as I said above, this really is a one-dimensional problem, so we should be able to do better. Let's think about the constraints that this pendulum is under. Number 1, we have this constraint that the distance from the origin is a constant L. Where is my origin here? Let's make it at the pivot. So R will be, R is equal to the magnitude of the position vector. Okay, and what we see is that the position vector of the bob is always has magnitude capital L, which is the length of the string. So right there we can see that there's going to be this nice constraint that the time derivative of r is 0 because r is a constant. So using our dot notation, we can say r dot is 0, and of course if r dot is 0, then r double dot is also going to be 0. In other words, only the angle changes. Okay. So that's motivating us to go from an x and y coordinate system to an r and theta coordinate system. Sometimes we prefer to use the symbol phi for polar coordinates. So then the question is, if we're going to do f equals ma, how do you write a in polar coordinates? In other words, the acceleration is r double dot, the second derivative of the vector. Now up here I said the second derivative of the position coordinate r is 0, but it's not true that the position vector has a second derivative of 0 because the position vector is moving, it's changing in direction. Okay. So we need to figure out how to write r double dot in polar coordinates. Well, let's go back to Cartesian. How do you write r double dot in Cartesian? Okay, so recall that the vector r is the vector xy, and so r double dot is simply x double dot y double dot. And recall this shorthand vector notation with the brackets is really indicating, is hiding, implicitly hiding the unit vectors x hat and y hat. Okay, so how about in polar? You might guess that r double dot in polar would be r double dot in the r hat direction plus phi double dot in the phi hat direction. In other words, the form would look the same in Cartesian and polar coordinates, but that is decidedly incorrect. And one easy way to see why that can't be true is phi double dot doesn't even have units of acceleration. So it can't be true. So what is the right way to write the acceleration vector in polar coordinates? Here's the bottom line, and then we'll show how we get there. So we've already seen that we can write the position vector as a distance from the origin times a direction. What we're going to show is that the velocity vector, v, which is r dot, the time derivative of the position vector, is has two components. It has an r hat component and a phi hat component. In other words, there can be velocity radially and there can be a tangential velocity. The radial velocity is given by r dot in the r hat direction, and the tangential velocity is r phi dot. That's like r omega. V, if you recall, v equals r omega, that's talking about the tangential component of the velocity. So we can think of this term as v in the radial direction and this term as the angular velocity, or the velocity in the not the angular velocity, but the velocity tangent in the tangential direction. So how about the accelerations? Well, the acceleration, which is v dot, which is r double dot, which also has r hat and phi hat components, but this time there's two elements for each of those directions. Okay, there's r double dot, the radial acceleration, or one piece of the radial acceleration, and then the other piece of the radial acceleration is r phi dot squared, r omega squared. That's you might recognize that as a centripetal acceleration, excuse me. And then in the tangential direction, there's going to be also two elements, r phi double dot, that's like r alpha, and then there's what's known as a Coriolis term that involves both r dot and phi dot. So collectively, each of these terms in parentheses represents an acceleration in the radial direction, and in the second case, a tangential acceleration. Okay, so this is the punchline, and we want to show how we get there. And along the way, we'll think about each step in multiple ways, but one thing we're going to have to deal with is the time derivative of the r hat and phi hat vectors are not zero, unlike the time derivative of the Cartesian vectors. So all of this complication comes around because although the time derivative of x hat and y hat and z hat are all zero, it's not true. The corresponding fact is not true for unit vectors in polar coordinates. So the time derivative of r hat is not zero, and the time derivative of phi hat is not zero. The lengths of r hat and phi hat are always 1. They're unit vectors, but their direction changes, and therefore their time derivative is non-zero. And that's why we end up with multiple terms in the tangential and radial directions. Okay, so we've now tried to motivate the use of 2D polar coordinates, and we've kind of signposted that there's going to be a little bit of complication in the rate of change of the unit vectors. In the next video, we will make that derivation for the time derivatives of those unit vectors to see where these velocity and acceleration expressions come from. So until next time, take care and be well.